just to, yeah, please go. Who is behind this Methane Mondays? So far, many participants are following this continuously, so you know already, but nevertheless, we have newcomers each time. So we have 3 organizations. We have 3 organizations. One is Energy Community Secretariat, which came actually with the idea to have this Methane Mondays, recognizing the need mainly in our contracting parties to have this education. But nevertheless, it's proven to be useful for many EU member states companies as well. Then we have GIE and Marco-Gas, both gas associations on Europe level, because we need expertise how to do this Methane Mondays. So far, we always actually were focused more on European issues, so we had several times discussion about upcoming regulation at the level of European Union. We had discussion on best practices of different companies, and we were dedicated a lot to actually how to monitor and how to assess and how to report about methane emissions. We also had discussions and webinars on different technologies, how to move from better to better level of monitoring methane emissions. But so far, actually, we didn't have this view from above, which we are going to have today. And I'm really very happy and very proud to have it. We invited many different speakers because, as you can see, many different projects and associations and companies are focused on emissions. For some, we have focus actually on greenhouse gas emissions. Some of them are actually focused only on methane, and also they are using maybe different technologies and different softwares how to analyze those data, and also having maybe different target users of those data. Today we will first have we will have Maria Berdal from Copernicus program from European Commission. And then we will have excellent and different speakers from different organizations. Yes, I can read the chat that actually the sound is not very great. So let's see if we can do something. But anyhow, I am just to stop, and then we will see if the sound is just related here with the Energy Community Secretariat computer, and hopefully this is the case, and then you will have a good sound from all other speakers. With that, I would like to invite Maria Berdal to start to share her presentation.
Yes, hello. Thank you. I will share screen.
And just to ask if the sound is now better with Maria, or is still some problem?
Yes, maybe I should speak a bit for people to be able to answer that. And also, I hope you see the right version of my screen now. I think you should be seeing only the presentation and not the notes. So
yes, presentation is in a bright format, and I'm happy that everybody hear you better than from Secretariat side.
okay. Well, so that's good. Then I will just start. So thank you for inviting me to this event. As it was already mentioned, I'm Maria Bardal. I work as a policy officer at the European Commission. I am seconded from the Norwegian Space Agency, where I also worked with the Norwegian implementation of Copernicus. But right now I'm working for DG DEFIS, which stands for Defense Industry and Space, in the unit of Earth observation, so mainly with the Copernicus program. My focus areas are the atmospheric monitoring and how Earth observation techniques can support the implementation and reporting on EU policies and regulations. And I also work a lot with Arctic topics. So let's go to the next slide. I will start by giving a short overview of the relevant EU policies concerning methane emission reduction. I understand that you might have had other Methane Mondays concerning this, but I will just give a brief overview. So the European climate law was adopted in last year, actually, states the Union's target of economy-wide climate neutrality by 2050, and also established a binding Union domestic reduction commitment of net greenhouse gas emissions. So emissions after deduction of removals. Of at least 55% below 1990 levels by 2030. And this was followed by the Union's 2030 Climate Target Plan and its impact assessment. The Climate Target Plan showed, on the basis of modeled scenarios, that achievement of an increased climate target of at least 55 net greenhouse gas emissions reductions in 2030 is feasible and would enable a smooth trajectory to climate neutrality in 2050. And the plan also highlights the need to step up reductions in methane emissions. As a part of the European Green Deal, the methane strategy was adopted. It sets out measures to cut methane emissions in the EU, including in the energy sector and internationally. So this leads us to the EU methane legislative proposal, which was adopted by the Commission in December last year, and is now in the process of being approved by the Council and the Parliament. While during this waiting period of approval, preparations on how to set out and implement and follow up the proposal are ongoing. So it is a part of the hydrogen and gas market decarbonization package, and it will regulate methane emissions in the energy sector. The proposal introduces new requirements in terms of measurements, reporting, and verification of emissions, as well as measures including leak detection and repair, and restrictions on venting and flaring. The regulation also puts forward rules to increase transparency on methane emissions associated with fossil fuel import. I hear some disturbance. Yeah, I will just continue. And the proposal targets the emissions arising along the entire value chain, apart from end use. So both Copernicus and the IMEO, the International Methane Emissions Observatory, coordinated by the UN, are explicitly mentioned in the proposal and will be involved in the work. And methane products from these two instances, data products, will be key for different parts of the implementation of the proposal. Most notably for Copernicus, the proposal states that there will be developed a super methane monitoring tool based on satellite data and products. It will be a hotspot monitoring tool. The details are still to be worked out, and the initiative is led by DG Energy. Earth observation can be an excellent tool to follow up on these strategies and ensure their implementation, especially when combined with other data sources. Satellites can measure the methane concentration in the atmosphere, but to find the emissions, we have to compare it to the predicted concentrations and use modeling. And we can also simulate different scenarios or emissions. Data from emission inventories are also fed into the models. Yes, so many countries are, as you very well know, committed to report their emissions, but the information is not exactly real time and can often be lagging by some years, and can also carry some uncertainties due to unknowns. This is why we use observations and compare it to predictions and models. So on to the space part. To give a short overview, Copernicus is the Earth observation component of the EU space program. The others being Galileo, and EGNOS for navigation, GovSatcom for secure communication, and SSA, the Space Situational Awareness, so dealing with space weather and asteroids and space debris. Copernicus is a collaboration between the Commission, ESA, the European Space Agency, and GEI-SAT, the European Meteorological Satellite Center. As for now, we have 8 satellites in orbit. They are called the Sentinels. Right now, one of our radar satellites, the Sentinel-1B, is feeling a bit under the weather, and we are not sure at this point if we will be able to revive it. Our dedicated atmospheric monitoring satellite, Sentinel-5P, is healthy and operating very well. Copernicus also consists of 6 different services. It's the land service, marine, climate, atmosphere, emergency, and security services. The satellites generate about 16 terabytes of data per day. And Copernicus has a free and open data policy, so the data and products can be accessed by anyone through the services or the Sentinel hub. So the most relevant service today for you here today is the Copernicus Atmosphere Monitoring Service. It is implemented by the European Centre of Medium Range Weather Forecast, ECMWF for short, and they also operate the Climate Change Service. COMS provides consistent and quality controlled information related to air pollution and health, solar energy, greenhouse gases, and climate forcing. The data covers everywhere in the world. COMS provides a wide range of different tools and forecasts, observations, such as global CO2 and methane monitoring, solar irradiation, and much more. On the photo here, you see the Sentinel-5P, so the dedicated atmosphere monitoring satellite. First, let's have a look at the global methane concentration, atmospheric concentration from 2003 to 2020. COMS uses observations from both satellites and ground-based measurement stations to monitor atmospheric methane concentrations. This tells us how quickly atmospheric concentrations are increasing. Using computer models of the atmosphere, COMS then uses the observations to estimate the strength of the various emission sources over time. So currently, COMS distinguishes between contributions from wetlands, rice fields, biomass burning, and other anthropogenic sources, and this service is continuously developed. So let's have a closer look at some of the specific methane-related tools in the COMS portfolio. So here we see the worldwide methane forecast. It shows expected concentrations in the world for the next 5 days, and it is updated daily. The global greenhouse gas analysis have a resolution of approximately 25 kilometers on 137 levels, ranging from the surface up to 80 kilometers over ground. The analysis combined the information from the modeled greenhouse gases with satellite retrievals of methane to produce a daily best estimate of the greenhouse gas concentrations in the atmosphere. Yes, retrievals of CO2 and methane, because the satellite retrievals are only available a few days later. The analysis is currently produced with a delay of 4 days. So, get the next slide. So the before mentioned Sentinel-5P satellite provides methane data worldwide with a resolution of 5 times 3.5 kilometers. Here we see the concentrations over the United States in 2019, and we also see a massive methane emission in Karachi in Pakistan. On the photo here. So as mentioned, it is essential to monitor or to compare against the forecast, also to neutralize biases such as due to clouds, surface temperature, and surface reflections, which also depends on location and season. In this project, the anomaly monitoring, we see the anomalies between methane observed with Sentinel-5P and the COMS simulations over the southwestern United States. So here the red dots indicate methane emissions that are observed by Sentinel-5P but are not present in the emission inventory data. So for example, unknown leaks. Green dots indicate methane emissions that are present in the emission inventory data but are not observed by Sentinel-5P. So reported emissions that are no longer there. The blue and yellow dots indicate differences between observations and model data that are due to issues with the observations. So it could be inaccurate surface albedo resulting in too high methane values, or the model. So darker dots show larger differences. Bigger dots indicate that more occurrences have been detected in the detection time window. So that was some of the current portfolio from COMS. But Copernicus is in ever development, and methane and other greenhouse gases are a focus area, as demonstrated with the EU policies. So Sentinel-5 is currently being built, assembled and tested, and will measure methane, NO2, SO2, O3 aerosols, and a few more. And then the CO2M mission, the anthropogenic CO2 mission, will measure CO2 and also methane, to be launched in 2025 and 26. And the Commission is also looking into different hybrid constellations, so smaller satellites that will support the larger ones. Some examples to be following this speech, and the Commission is also looking into developing its own hybrid constellations. And then along with the CO2M satellites, a new service element in COMS will be developed to provide policy products and tools to monitor anthropogenic CO2 and methane emissions. So that was it for me for now.
Thank you very much, Maria, and that was exactly in 15 minutes. Very appreciated as opening, and I am glad that actually you set somehow the scene for further presentation and providing the link what we have before with all this EU upcoming legislation. So with that, I would like to invite Mr. Stefan Germain from GHG Satellite company settled in Paris, I believe, to tell us more what this company and these satellites are doing and are able to provide.
Thank you very much, Carolina. So thank you very much for the opportunity to present today and to give you a bit of an update on what we at GHGSAT are doing and how that complements what Maria just described in the previous presentation. So at GHGSAT, we use our own satellites to monitor greenhouse gas emissions from industrial facilities around the world. And the key distinction versus what you just heard is that we measure down at the facility level. So instead of trying to cover the whole planet every day, as the Copernicus missions are designed to do, our system is really designed to focus in on specific facilities and identify the specific sources of emissions, primarily anthropogenic, but in some cases even natural sources. So we not only use our own satellites, but we also use aircraft sensors to monitor greenhouse gas emissions. And then we apply analytics to our measurements combined with third-party data, including the Copernicus satellites, to arrive at valuable insights for our commercial and government customers. Just last month, after a rigorous 2-year review of our technology and results, the European Space Agency awarded GHGSAT with a third-party mission status, which paved the way for a closer collaboration with Copernicus. So we're very happy about that, and we believe it reinforces the kind of hybrid concept that was mentioned in previous presentation. So this is an example of one of our satellite measurements, and immediately you can compare this to what you just saw in the previous presentation and see the difference. What you're looking at here is an image of the Permian Basin in Texas. It was one of those anomalous areas that was highlighted in the previous presentation in the United States. And you can see the background is just a standard visual image that we took from a public source. And every one of the white squares in that image is effectively an oil and gas facility. And many of the white lines between those facilities are either roads or pipelines. And so every single one of those is a potential methane source if there's an anomaly in the production environment. And overlaid on the visual background is the methane. And so that's what you see in false color. So in red, yellow, green, and blue, with decreasing concentrations going from red down to blue. And so it's immediately apparent where the methane emission is. And within this roughly 8 by 8 or 10 by 10 kilometer window, it's immediately apparent that one of the facilities is emitting and not all the other ones around it. And then we zoom in on the right to give you an idea of the kind of resolution that we can get. So this kind of attribution is what is really important for operators to understand, exactly which facility is emitting, and therefore is also actionable because you're not sending the wrong operator to the wrong facility to fix something. We can do this everywhere in the world, and we do it using nanosatellites, so using satellites that are about the size of a microwave oven. And so that's about 100 times cheaper, if not 1,000 times cheaper in some cases, than public satellites. And therefore, we can afford to launch more satellites at a fraction of the cost of large constellations. Today, we have 6 satellites in orbit. We launched our first one in 2016 as a demonstration, and we took everything we learned in that first one and applied it to our next 2. And then finally, we launched 3 more about 2 weeks ago. And so we have another 7 in constructions behind that with launches in Q1 and Q4 2023. So again, the advantage of having small satellites is that we can deploy and iterate our technology very quickly and improve on the performance that will deliver the performance that you saw in the previous slide, but also improve on it very quickly. And at all times, we want to work in collaboration as a complement to the large agency satellites. So in 2021, we performed hundreds of thousands of measurements from tens of thousands of sites and identified thousands of methane emissions worldwide. The map below shows where some of the largest methane emissions were found in 2021 from oil and gas, coal, and landfills. And the larger the red circle or the orange circle, the higher the emission rate of the source. So we've detected so many sources that we can look at a detailed trend around the world. And perhaps one of the most startling trends is to look at total emissions over time. And this chart looks an awful lot like what you saw in the previous presentation, although obviously taken from a completely independent source. And unfortunately, it just reinforces what I believe we all know, which is that total emissions are increasing worldwide. The difference here is the way we measured this is directly from facilities and the number of emissions detected from facilities, as opposed to what was in the previous slide, which was really looking at atmospheric concentrations. So the two obviously complement each other and provide some pretty powerful evidence that we have a continuing issue that we all need to address. All right, there's nothing more compelling to understand what is out there than take a bit of a video tour of the world. So I'm going to start with by far the most active region for methane emissions worldwide that we saw, and that's in Central Asia, and in particular in a country called Turkmenistan. So in Turkmenistan, there are over 80 super emitting sources and ultra emitting sources that we're tracking right now. I decided to focus in on one just to give you an example. So this is just a standard visual image of this facility. And if we overlay 6 months worth of methane taken with our satellites, you can see just how active this particular site is. The reason that methane plumes blow in different directions on different days is simply because the wind is shifting around. But also from this, you can see that it's not just one facility. It's in fact many different sources and facilities around this one area. And this is what we find to be quite typical in Central Asia, not just Turkmenistan, but other areas, which then lead me to perhaps go explore other areas in Central Asia. So not only do we see significant emissions in Turkmenistan, we also see significant emissions in neighboring countries like Kazakhstan. And in this case, we'll just zoom into Uzbekistan. and take a look at a particular area again. And you see here just one example of the many that we found in this one area. So you're probably seeing a pattern now that we often see clustered emissions from areas. So a low resolution satellite that can only see 5 by 7 kilometers or so per pixel wouldn't be able to distinguish the individual sources or the individual emissions in this particular area, whereas this is exactly what our satellites are designed to do. So moving on from Central Asia, next question might be, well, where are the next greatest oil and gas emissions that we saw in 2021? Perhaps in Russia or the United States, Middle East. Well, in fact, the next highest emissions we saw were North Africa, which obviously has significant implications with regards to energy security for the European Union and where gas is being procured. So this particular area in Algeria is a constant emitter, in fact, not necessarily each individual source. They tend to be intermittent and change, but in aggregate, we see emissions almost regularly in this particular area of Algeria. So if we move out of Algeria and then go look at other areas of the world, again, where there's perhaps the most significant emissions in the world of methane from oil and gas, and now I'll focus in on the United States. So within the United States, the most prolific area of methane emissions is the Permian Basin, this area in Texas and New Mexico. It has a very dense area of production, as you can see by all the white dots in that image. And that's why it is so important to have high resolution, to be able to really pick out the needle in the haystack, pick out the individual site within all those clusters of sites that is responsible for the emission, and which operator within all of those is the owner or operator of that site. So we often get asked, what is the limitations of satellite monitoring, and our satellites and Copernicus satellites and third-party satellites, and often one of the most significant ones that is raised is light and whether or not we can actually see northern regions. And the answer is yes, we can absolutely see the North Slope of Alaska, or in this case, the Yamal Peninsula in Russia. And we routinely see emissions in this area as well. Moving on, if we then go look at potentially different types of sources or areas with significant emissions, we focus in on China, because in China, although there might not be significant oil and gas emissions, there are extremely significant coal mining emissions. In fact, the largest coal mine emissions in the world are from the Shaanxi province in China. So here you see these large bubbles, but they overlap, and there are many, many small sources within it. But even in China, there is oil and gas, and in this particular area, in the Daqing part of China, we see regular emissions from this one particular oil field. Moving on, and again, perhaps thinking of other sources of emissions. So we've talked a lot about oil and gas. We've touched a bit on coal mining. Next is landfills. We see landfill emissions all over the world, but no emissions are greater than the ones we see in India. We routinely detect large emissions from landfills in India. But even in India, there's also oil and gas development. In this one area here, we again routinely see emissions from a series of oil and gas developments, and we track and report that to the operator in the region. All right, so I probably need to stop there for sake of time, but just want to give you an overview of some of the things we saw around the world. And I can tell you that the trends and the emissions that we're seeing in 2022 are only increasing. So perhaps just one quick slide to differentiate between what we see and what other satellites see, both existing and future. So there are today about 10 satellites in orbit, 6 of which are ours, that have methane detection capability. And there are many more coming, and you'll hear that from some of the speakers coming up after me. But it is important to realize that they are complementary in their capabilities. And even if they have different objectives, they can be used together. So in the first presentation, you heard a lot about the Copernicus constellation and the satellites that are on the left here that are described as global mappers, or ones that can see the whole world every day and are really used for scientific and policy purposes. On the far right is the ones that are designed for detection and repair. And GHGSAT, our satellites, were designed from the get-go exactly for that. So they have extremely high resolution, and have very low detection thresholds compared to the other satellites. And today, we're the only ones in orbit with this capability, and we're specifically designed for this capability. And in the middle, we have a new class of satellites that are being developed, and some that have been launched would have the capability for regional monitoring. And so there's one eagerly anticipated mission coming up called Methane-SAT, which will be looking at total emissions increases and decreases per basin, not just in the United States, but in other parts of the world as well. So again, I want to emphasize that these satellites are complementary in almost all cases, and where they're not complementary in technology, they're complementary in coverage, because there are so many sources worldwide that need to be monitored on a regular basis and as often as possible, that all the capacity that's available from all the satellites today can be used together. So that leads me to the key point I want to emphasize perhaps the most in this presentation, which is that we have an opportunity to work together. Really, we have a shared purpose, which is to, at the end of the day, mitigate climate change. So competition is good, and we're happy to, compete with, in all environments. But I do believe we have a shared purpose, and to achieve that, we need to avoid confusing stakeholders. So how can we do that? Well, so first we have to work with and collaborate with global institutions by sharing all of our data with a neutral aggregator, and that's the IMEO. I think everybody on this call is aware of who that or what that is, and we are a strong supporter of the IMEO. But second, we need to subject ourselves to the rigor of third-party review and validation. We must accept peer-reviewed blind verifications of performance claims. We can't just blindly say, or use fancy marketing presentations saying that we can achieve fantastic things and not have data and science to back that up. So whether we use our own satellites or third-party satellites, we need to do blind verification of performance claims. And until we can do that, we should all at least caveat our claims to avoid confusing the market, because if we confuse the market, we do all of ourselves and others a disservice. So in the end, we need to create impact, and there are opportunities for mitigation all over the world. So we found that when operators hire us to monitor their emissions, they usually act on what we find, and so we get a significant amount of mitigation working with our partners. However, when we find emissions from sources where operators did not hire us, our success rate is much lower, but not zero. So altogether, these efforts have led us to mitigations of over 2 megatons in 2021, and we expect to do far better in the very near future. All right, to wrap it up, I'll just summarize by saying that satellite monitoring today is a reality, and it will only get better. Global transparency using satellites is a reality today, and again, it will only get better. So thank you for your time, and I look forward to answering any questions later on.
Thank you very much, Stefan. It's a really great presentation. I would put some of your slides at the end as a conclusion, because that was the question continuously popping up. Like, we have so many projects, and then how to avoid competition and how to actually achieve synergy. But you partially answer to it. So let's move. Keep the question for the end, and let's move to the next presenter. This should be Methane-SAT actually, but I don't see Steven Hamburg among participants or his assistant. So if there is somebody else from Methane-SAT, I would like to invite him or her to deliver presentation now. If not, then we are moving further on. I mean, from Brussels to Paris, but then from Paris to Spain. And with that, I would like to invite Manuel Montesino to deliver presentation on Satlantis. So to see what is going on both sides of Atlantic Ocean. Manuel, please take the floor.
Thank you very much, Carolina. And let me share my screen. So can you see it? Can you see my screen?
Yes, perfect. We can see the screen and it's in presentation format.
Okay.
So please go on.
Okay, so thank you very much for this opportunity. My name is Manuel Montesino, and I am an image processing engineer at Atlantis. And in the following minutes, what I would like to do is to present a project which is called GEI-SAT, which is a project of Atlantis in order to get advanced and reliable measurements of methane from space. So as you probably know, 50% of the methane emissions come from small sources. So in order to be able to measure such emissions, it is key for any detection device to have, we identify three key aspects. The first one would be low detection threshold, as was mentioned before, to be able to detect the smallest concentration of methane possible about the background levels. We also need a high resolution image because with very small pixel size, we can identify the smallest point sources of fugitive emissions and their exact location. And also we need a good spatiotemporal coverage to be able to surveil those regions of interest, so we can cover wide extensions such as gas pipes and ensure a good frequency of revisit for timely detection. And this is especially true with intermittent emissions. So our contribution for the challenge is the GEI-SAT constellation. And the goal is to provide the lowest detection threshold and smallest pixel size of the market. That's our goal. So in order to face the challenge, GEI-SAT encapsulates three major technological innovations, I would say. The first one is the optimal design of filters. So where in the spectrum we are looking at. So they are specifically made for the detection of methane, and also considering some other atmospheric components that could potentially bias the measurement of methane. GEI-SAT also contributes with the high spatial resolution, thanks to the technology of the ISIN cameras and their observation strategy. We can get a very small pixel size. And the last one is what we call the agility of the satellite. That is the ability to point the camera, which is in orbit, towards specific targets like facilities for long times. These three aspects, we think they can contribute significantly to lower the detection threshold of Atlantis multispectral cameras. So as an example, you can see on the left a simulation of the detection of methane using Sentinel filters. These are the two images. The Sentinel filters, the result from the Sentinel filters are the image on the left, and the result with the GEI-SAT optimized filters are the images on the right. Both images correspond to an oil and gas facility in Algeria with 2 known leaks of methane, which are these 2 red dots. So you can see on this comparison that thanks to the optimized filters of GEI-SAT, the satellite would improve the detection of methane thanks to a higher concentration of higher contrast, of the plumes, which you can see here as dark blue clouds, in comparison with the signal from the background. Regarding the satellite resolution, there is the literature, the scientific literature states that there is a nonlinear relationship between the pixel size and the signal from methane. That is, the smallest the size of the pixel, the much higher the signal from the plume will be. This effect is visible in the results from a scientific publication carried out by Sanchez Garcia and colleagues. And to detect methane, they use world view images with 3.7 meters resolution, which you can see here. And Also, they created the 30-meter resolution equivalent, which is this one on the right. So to detect, from the results, you can see that the signal of the plume of methane gets diluted with the background. We have a point source with very high concentrations in a very specific region, and that signal of methane gets very quickly diluted with the signal from the background. So then the signal is not so strong. So much so that the smaller plumes of methane with high signal in the high resolution image, which you can see right here, they can go completely unnoticed in the low resolution image. So the third key aspect, and sorry because okay, here it is. The third key aspect is our proposal is the agility mode. So this is basically the ability, as I just said, to point the camera towards a specific target. I don't know if you can see the video properly. So basically, what you can see on the image is how the satellite is pointing towards specific targets. In this case, there is a coast, but it could be a pipeline. And this ability to point the camera towards these targets has several advantages. First, it reduces the time of revisit because we don't need to wait for in a specific orbit to pass over our region of interest at nadir. We can simply go and point up nadir and look at the specific facility. It also reduces the detection threshold because we can take more images in a given area for longer times, or we can increase the exposure time of our acquisitions. And both increase the signal to noise ratio of the image, and therefore they lower the detection threshold of our devices. So this is our plan for the future. Our plan is to build a constellation of satellites with these characteristics that I just mentioned, which are basically be devoted to the detection of methane, basically or mostly from oil and gas facilities. So the satellite in the sequence, they will progressively expand the spatiospectral capabilities of our cameras and improve the detection threshold and reducing the time of revisits. So as you can see on this diagram, the first satellite is going to be the GEI-SAT precursor. This is a 16U CubeSat with 2 channels, visual near channel and a SWIR channel, shortwave infrared. And the SWIR channel goes up to the spectrum into the 1700 nanometers. The linear will provide the context for that particular scene at a spatial resolution of 1.65 meters. And the spatial resolution of the SWIR channel is going to be 30 meters. So the detection threshold of the satellite this is just an estimate, and we think, or our goal is to be around 150 kilograms an hour. GEI-SAT precursor will be launched in the second quarter of next year and will be operational by the third quarter of that same year. 6 months after, a new satellite called GEI-SAT Plus will be in orbit, and it will be heavier and with a larger telescope. It will provide symmetric resolution images in the linear part of the spectrum and a 7-meter resolution image in the SWIR. With these new capabilities, the satellite will lower again the detection threshold to, we think, around 100 kilograms an hour. And then finally, during 2024 and 2025, we are planning to put in orbit 3 new microsats. And their size basically will be the same size as the one before, but here the novelty is going to be the spectral range, which is going to expand to the 2300 nanometers. And again, we hope that this new feature of the satellite will reduce the threshold to about 50 kilograms an hour, although this is something that we still need to confirm. So GEI-SAT precursor is now under development. The satellite is nourishing from the experience with our first Satlandis mission called Urdaneta, which launched last June. And the precursor will improve the specifications of Urdaneta in some other aspects, such as the generation of electrical power, the speed of data transfer from the satellite to the ground, and better attitude and orientation control system. The design phase of the payload is coming to an end, since the payload will be delivered for the satellite integration at the end of this year to be ready for launch in spring 2023. So in this GEI-SAT precursor, there are two main concerns in this project, which are the development of an optimal design of the payload and obtain reliable measurements of methane concentrations and flow rates. And as a result, the project was organized in these three phases you can see on the screen, following a bottom-up approach. So the project contemplates the development of 3 camera models. The first one would be the engineering model, the second the plane model, and the third one is the flight model. Each model benefits from the cumulative experience, hands-on experience with the previous one. And in this way, the scientific team in Satlandis can deal progressively with increasing levels of complexity. So the engineering model, which was basically the first development, it is a camera with, it's a camera with 2 COT sensors and lenses, together with a set of filters that we specifically selected for methane detection. And this camera was repeatedly tested in the lab and in field trials during 2020 and 2021. This is how we started with the engineering model, or EM for short, first taking measurements at a very close distance in the lab, where we had control conditions regarding the light intensity with an integrating sphere and the pressure, temperature, and quantity of methane inside a gas cell. We were able to test the filters and the sensors and check the signal intensities and verify the ability to retrieve the concentrations of methane from those images. So then we moved the engineering model, or EM, to the field. That is this second point. And first, we placed the camera at a 4-meter distance from a highly reflective surface, which you can see on the image. And to the surface was attached a plastic duct that released methane freely from a gas tank. Here we evaluated the different camera configuration, parameters, and the simplest detection and retrieval method, together with an automated cloud masking algorithm. And the results, one of the results you can see here right now. Then progressively, as you can see, we are moving a little bit farther away. This time, the next experiment was at 40 meters distance with a little bit more challenging background. At this longer distance, the pixel size is larger, and also the amount of atmosphere we have between the target and the camera is also thicker. So we evaluated previous detection methods and the quantification techniques, and tried new ones a little bit more sophisticated. Then from the lessons learned, we built another camera model, which is the plane model, at the beginning of this year, 2022. And the plane model, or PM for short, is a redesign of the engineering model with a slightly different set of filters. And the EM incorporates a closed version of the optics and the electronics of the telescope. The camera is being tested or is going to be tested during the second and third quarter of this year in several campaigns, which are going to take place in Spain and the United States. First, we are flying over Enegas facilities, which is a gas company here in Spain, during the second quarter and third quarter of this year. And then we will go to an oil and gas facility in the United States. We are also participating in an ESA campaign this summer to fly over landfills in Madrid and test our detection threshold. So in preparation for those events, we tested the PM on ground, as you can see here. This is the PM. And here we place the camera at a 1,000-meter distance from the gas stand I mentioned earlier. And the main goal was making the electronics and software to work properly for those tests. Although we confirmed the capability to detect the small plume of the gas tank from a quite long distance using the simplest detection strategy at the same time. At the beginning of May, we flew the camera, the PM, over a gas compression station, one of the many that Enagás has, during a couple of days, and the camera was mounted on the side of a helicopter, which flew at an altitude of approximately 25 to 3,100 meters over the facility during maintenance operations. And for the test, there was a third-party company called Viragas, which was involved in the test, who provided independent measurements of the emissions from the ground. Sorry, so we could cross-check our estimates, and well, this is some data that we are still processing, but so far I think we're very happy with the provisional results that we are getting. Now again, once we finish those first group of campaigns, we are going to build what is the flight model, or FM, by the end of the year, when the model will be delivered for its integration into the platform, and the launch of GEI-SAT precursor is scheduled on the second quarter of 2023. Now, the three phases of the design are being supported by end-to-end simulations. So these are a sequence of computer models that tests the various design and algorithms under several emission scenarios, accelerating the development through very fast iteration. Additionally, the model helps the science team to become familiar with the physics of the problem or support the planning of the measurement campaigns. In this slide, you can see the structure of the model that we use in a very visual manner. On the left, we can see the first model, which generates the observation scenario. That is a model that calculates the solar radiation that reaches the sensor of the satellite from a spatial domain on Earth, based on the land use below, the weather conditions, the atmosphere, and the illumination conditions as well. Then this information is used by another model that generates the raw frames captured by the sensor, considering the telescope's configuration, such as orbital altitude, exposure time, frame rate, or the set of filters that we want to test. And then over those frames, we apply our processing pipeline for methane detection and quantification, and then we get to the final estimates of flow rate, which we can compare with the input value to see how well we are doing. With this structure, we can iterate very quickly, tweaking the camera configuration parameters to maximize the detection layer in the processing pipeline, and also improve these algorithms that we use for the analysis to get better estimates and evaluate the weight of various sources of uncertainty. So basically, all these efforts are oriented to make GEI-SAT an end-to-end solution for methane detection and quantification. And the solution that we are proposing contemplates from the development of a scientific grade payload, which is what we call the upstream, up to the final product, which is the reliable and tailored information about methane emissions, or what is usually called the downstream. It implies that in addition to the satellite, we also look forward to build a data center and a user platform for our customers. And the role of this data center will be receiving, storing, and processing the satellite images coming from the ground stations. And then at this point of the process pipeline, we can combine the information from the images with public data sets, or maybe complementary third-party data from bottom-up measurements, such as ground sensors or drones. And finally, through the user platform, which is the last step, the customer, in this case, NIS, will have access to what we hope real-time information, thematic maps and visualizations and dashboards defined by their preferences and their needs, like, for instance, producing periodic oil and gas reports. So that is basically what Satellite is doing, and the way we want to contribute to this detection and monitoring of fugitive emissions of methane. Thank you.
Thank you, Manuel. You provided somehow view from another side, also important from Earth to the space, and from space to the Earth. So we will also save the questions for later on. And now I would like to invite Antoine Rossam, president and founder of Kairos, to take a floor and to show what this company is doing.
Okay. Please, can you stop your sharing, please?
I think it's already.
Can you see me? Hello. So
yes, all fine. All fine.
Okay, thank you. Yeah. So the idea, is to elaborate on my colleagues have been saying. So Kairos, we are a geospatial company with offices in Houston, Paris, London, Singapore, New York, and Bangalore. And what we do is we do software. So we are not an operator of satellite. We are a pure software company. We are source agnostic, and we basically have created pipeline to look at all available satellites to detect menacing on Earth, the impact of human activity on Earth, including externalities like methane emission. So if we look at methane, there are basically two key methods to measure methane. One is at the basin level. It's a full basin inversion where you need to have a prior, and you can look at all the emission coming from one basin, and looking at the evolution over time of the methane emission at the basin level. So that's the top one. And the second one is, point source detection, super emitters, with a specific detection threshold. So we are at Kairos, we are developing both methodologies to one, quantify all the methane coming from one region, like the Permian Basin, and secondly, to detect on a global basis all hotspots that can be detected. We have been published in science magazines, so the science is very solid these days. And the conclusion of the science magazine is that Sentinel-5P, detects ultra emitters, which represent approximately 10% of total emission from the oil and gas sector. And there is a power law, which means that super emitters is a good indicator of the methane emission in a specific region. And obviously, the conclusion is that it is urgent to start eliminating these ultra emitters. It is a priority because they are relatively low cost, of mitigation. To stop these super emitters is pretty easy. In terms of science, there has been a study organized by Stanford in blind test, and at Kairos we have been using all commercially available data, World War III, Sentinel-2, Landsat 8, and Prisma. We had excellent result. We had no false positive during the experiment. The detection threshold is 1,000 kilo per hour, and there is no systematic bias. So, I mean, that was an excellent confirmation from the blind test that monitoring satellite that goes over the world on a regular basis, so every day for Sentinel-5, every 3 days for Sentinel-2, 8 days for Sentinel-8, can detect methane and quantify methane leaks. And the good news is that we can attribute these leaks because of the resolution of Sentinel-2 and Landsat 8. Now, we'll go quickly through how this works in our platform. And I'm going to share another screen.
Hi everyone, so this is Romain Vadon. I'm a senior analyst in the emissions team working on methane emissions detection, and I will just show you a little bit the demo about what we can detect around methane. So what you see here is our platform where we basically gather all the detection of methane supermeters using a satellite from the European Spatial Agency, naming Sentinel-5P. So as you can see, we have an historical of detection since early 2019, and it represents supermeters. So as Antoine said, these are the largest emissions, representing 10% of the total oil and gas emissions. But as you can see, there are still plenty of them that are detected very frequently. So if I show you maybe an historical month by month, you can see that there are really frequently this type of detections that can be captured by satellites. We usually get around 20 methane supermeters per week, mostly from oil and gas and coal activities. So maybe if I go into some examples, as you can see, the orange dots are mainly gathered in specific areas of the world, which corresponds mainly to the regions where hydrocarbons like oil and gas and coal are produced or transported. So if I zoom in, for example, Middle East and especially Iraq, you see that you have large orange dots which represent the largest supermeters with the highest global warming potential that we've detected. So for example, if we take this one, which was detected back in July 2019, you can see that the plume is pretty large. It's a very wide detection that is going very far from the source, even above Kuwait. It was basically quantified by our algorithm around 500 tons per hour, which represents more than the annual emissions of 100 cars in the US, to give you an example. So if we maybe take another example, in Russia, you'll see that you have a quite interesting schema of detections, which are basically in the same route than pipelines that are supplying Europe in gas. So we see very frequent and very large emissions, which are usually linked to maintenance or incidents that provokes some actions, some urgent actions from operators that usually relies on just letting the gas be released in the atmosphere directly, which results in very high concentration of methane that we can see from satellite images. We have several of them that have been also confirmed by operators. For example, Gazprom has confirmed that some of these detections were really provoked by their activities, and also confirmed the quantification. So maybe if I zoom in one of them. Yeah, so here you can see the typical schema of detection that we have.
We lost you, I think. We can't see you anymore.
Sorry. Yeah, should be better now. So this is a typical schema of detection that we have around pipelines, which is basically two subsequent detections of leaks that are on two valves of the same pipeline. And this one was detected on September 2019 at an emission rate of 60 tons per hour. Which is quite interesting is that we tested on this specific location and these specific dates if we could have a look with other satellites with a much higher resolution, if we could see something. Because here Sentinel-5P is just giving you the suspect areas of detection with a resolution of around 5 kilometers. If we look at Sentinel with Sentinel-2, the satellite has a resolution of 30 meters. So if I just show you the same location, so if you zoom out, you realize that it's the same location of the pipeline. And we have an image of Sentinel-2 at the same dates. And you can see that here the detection is much easier to see and to track where the source is. So you see the high plume of methane in yellow and purple. And if I just overlay the RGB image, so the basically Google Maps view, you see that here we are around on pipeline and on a specific compressor station that leaked that day. So this technology, we use it to basically detect at the asset level the emissions of methane. And it's pretty interesting in areas where you have very dense assets and production activity. So if I go in another region, which is the Permian, I think we've spoken about it in before. But this area is really interesting because you have a lot of infrastructures to produce, store, and transport oil and gas. So as you can see here that you have a lot of different infrastructure in the same area. And if we look at one image of a detection with Sentinel-2, yeah, so we can see that we see quite easily the emissions here in yellow. And if we zoom in, we can identify the suspected assets which leaked that day in November 2018, which is basically also a compressor station in the root of a pipeline. So this technology is really useful for us to do asset level. I mentioned Sentinel-2, but we're also trying to apply this technology using other satellites. For example, we are applying it to Landsat, which is a satellite developed by the NASA. And it provides pretty good results, and it helps us having a closer look to asset level detection. It's not like Sentinel-5P, you don't have an image every day, but you have a revisit of up to weekly, which gives you a pretty good overview of the annual emissions of a specific asset. Maybe if I finish with the other type of data that we provide around methane. So this is a second methodology that Antoine was telling about, which is regional inversion. So as you can see here, there are several areas in blue, which are in fact areas where hydrocarbons are produced, either coal or oil and gas, and where we can see a lot of emissions continuously being released in the atmosphere. So if I take once again the example of Permian here, and if I go down, you can see that we have an estimation every quarter of the total emissions of the area related to oil and gas. How do we do that? Basically, we'll use all the images we get from Sentinel-5P in the area. Using wind data and atmospheric simulation, we'll be able to trace back the emissions in the area. And we also have the information of the activity in the region using satellite detection of new pads being drilled. This helps us deriving an estimate of the total emissions with a certain confidence interval that you can see here in black. But it gives us really good trends and really interesting trends on the total emission of the area. And here specifically, you see quite clearly the drop in emissions related to the drop in production in the COVID early stage in 2020. And the worrying fact is that we see a bounce back of emissions since then with very high volume detected last quarter. That's it on my side.
Thank you. So if I go back to my presentation, what kind of conclusion can we draw from that? The problem when we have this data set that we have been having for a couple of years now with the full coverage of the full world is we really want action to happen, and we have a partnership with Bloomberg where they investigate on a regular basis the detection we have, and they talk to the operators who always confirm our detection and our rates, which is good for obviously from a technology standpoint. But what is more importantly, it raises awareness that there is now a spy in the sky that can really spot large emission of methane at any point in time. The good thing is that unlike the satellite that our task can cover only a small part of the world every day, we cover the full world every day. And this is why our technology has been put forward by Kadri Simpson, by John Kerry, and by Emmanuel Macron. It's a key tool for policing the methane world. We are also a key input to the IEA methane watch, both from super emitters and basin inversion. We are, the fuel behind this publication, which is the reference today in terms of methane. So clearly, we have been able to really increase the quality of the data around methane in the energy industry. Now, the worrying trend is that we see an increasing number of super emitters between 21 and 22. And what is even more worrying is that if we look only at the global methane pledge participating countries, there are a number of super emitters, which is a clear indicator of global emission, is increasing as well. So it's a 20% increase. So the methane pledge, is for now a nice word, but it is not getting into action. And when we see the very short, time frame we have to reduce our, to reduce our consumption of CO2 budget, this is clearly something that is not, a very positive signal. If we look at coal, we see a lot of emission. We have been seeing a lot of emission. We had 45, super emitters since 2019. Above the Raspadyaska mine, the maximum rate was 153 tons per hour in July 2019, a pretty heavy one. So coal is clearly part of the play, not only oil and gas. And as was mentioned before, if we look at the basin level, the Permian as well is also increasing since the COVID. So there has been a lot of there was a methane moment at COP26 with this methane pledge, but unfortunately, this is not getting into action. So in terms of conclusion, is satellite monitoring is not it's not rocket science anymore. This is operational. We cover the full globe every day. We detect things that are proven. It is used. It is working. Now, what we need to do, and this is why we are partnering with IMEO, it is to transform that into action where operators will be notified, and at some point in time there will be either a border adjustment mechanism. In Europe we have the tool to create a CBAM on methane now, or regulators will impose fine for operators who do not respect the rules. So this is really, we have the tools, and in our opinion it's really time to act. So this is the end of my presentation.
Thank you, Antoine, very much. So we put again in proper framework everything, because I mean, monitoring data is one thing, but then to react and to decrease all these emissions another one. But yes, everything goes hand in hand. In the meantime, Steven Hamburg joined us, and I just found out that actually he's at home with COVID, but still willing to deliver a presentation on Methane SAT, and I am really very grateful to him for that. So Steven, if you can share your presentation.
Yes, thank you very much, and my apologies for being late. It's been a challenging weekend. See if I can hopefully here figure out how to share. At the moment, hold on one second. Figuring out how to do that. So I picked most of, just trying to see if I can do this. That helps. Having trouble finding it. Yeah. Is there a trick to doing it? Again, my apologies. I'm not functioning quite at my normal. It requires me to open system preferences.
If you wish, you can send presentation to us, and then we will run it. And then in the meantime, we will have Sean Donegan delivering presentation. If this is fine for you, or we
yeah,
will...
go ahead and I'll try and figure out.
Okay. Then Sean, please deliver your presentation now to see about another software, how to analyze all this data, and then we will go back to Steven.
Okay, well, good afternoon and good morning, everybody. My name is Sean Donegan. I'm the president and CEO and founder of Satalytics. We are based in Perrysburg, Ohio, or as we like to call it, the 751st most visited city in the nation. And I hope you are seeing, well, let's just...
We see slides, but not in proper presentation mode.
Can I have confirmation of that? Yes.
We saw slides for a moment, and now they disappeared.
Okay, let's go back to sharing. Easy.
Good, perfect. Now everything is fine.
Okay. So Satalytics, as I said, is based in Perrysburg, Ohio. I think we're slightly different to many of the folks that you've spoken to before, or you've seen present before, because we are a pure software company. We're actually agnostic to the data set, where that data comes from. But like many of the others, we are using remote sensing to the fullest extent, the power of the sun shining on the Earth's surface or a body of water. And of course, we are looking at both the absorption and reflective signal, as many of you will know. But being agnostic to the data source, we had a few goals in mind when we first started looking at methane now, which dates back 8 years. Our first early adopters of methane were Anadarko, BP, and also energy transfer partners, oil and gas companies, which is where we started life. And we started life looking at the north slope of Alaska with BP, with 25,000 bodies of water for other contaminants. Our goal was always as a company to get to quantification. So whether we're looking at vegetation health, tree height, methane, we're just about to release our CO2 algorithm. We always wanted to get to quantification, and we always wanted to use the highest spatial resolution that was available. So to us, we don't care whether the data comes from a satellite, a drone, a plane, a fixed camera. The one focus goal, though, that we wanted is if we could detect elements in their infancy, then we would minimize the impact that followed on. So if we can detect a methane leak in its early infancy, then clearly if you're leaking methane, you're not selling that gas. Number two, consequences of leaking methane, as we're all well aware and has been discussed ad nauseum on this, obviously has tremendous impacts around the world. So anything that we can minimize therefore lessens the blow. That's sort of the theory behind it. And with that with that sort of goal in mind, for our clients that we deal with today on a regular basis around the world, we produce the results within 3 to 4 hours of collecting the data. So turnaround was critical for us. And that really leads you to only one platform, and that's satellite, and the infrastructure that it can cover in a very short area. So as a company, we task satellites. We are using for methane, we're using WorldView 3, we're using 3.7 meter spatial resolution. Quite frankly, I'm staggered that that hasn't been more adopted around the world, but I'm sure it will as we go. BP has blind tested and studied satellites in some 65 countries around the world, different backgrounds, different environments, different weather conditions, different seasonalities. And in fact, just last week, our largest customer in the local gas distribution arena, which is Duke Energy, had a whole series of academics out in the field showing them the results, and literally going out and ground truthing and field testing, as they've been now using satellites for a couple of years across that arena. What we're banking on going into the future is that there will be ubiquitous data flows from a variety of different resolutions of satellite. We've had our global methane, which shows you the hotspots and uses Landsat and Sentinel for many years. In fact, it was one of the it was where we founded some of the data and some of the average data that we looked at when we first started to look at methane. And of course, as has already been discussed, those are available and are free, but you know, they're still at very coarse resolution. So we task most of our company's assets that we're looking at, and we task that using WorldView 3 in this particular case. And I thought it would be interesting just to sort of qualify a couple of elements that you've already seen today. And that is, if you look at the spatial resolution from sort of left to right, it shows the same scene. And by the way, we'll see this live in a second. So you literally see a CEO operating software live, not based on video. And you can see here that to the far left, 100 meters by 100 meters, looking over a large set of assets, really doesn't give you much detail. In fact, truth could be said that in the middle, while Sentinel and Landsat are good satellites and others, it still doesn't provide the granularity down to the source that you could potentially have. And on the far right is the WorldView 3 3.7 by 3.7 meter using satellites. We measure both the plume and the flow rate with a pretty high degree of accuracy. As a company, we have over 40 different algorithms because, again, we don't believe that methane is the only thing that will keep you up at night. And even if you get to net zero, which is highly doubtful, there will be some carbon offsets. So now you're bringing into the equation, looking at vegetation, its health, its height, the tree speciation, etc. but we have a plethora of algorithms that can run at the same time to try and solve most of those pressing issues, methane being one of which, CO2 being hot on the list, and we're actually working on a hydrogen algorithm with one of our customers as we speak. The goal for us, though, is that from one set of data, you should be able to use it for a number of different challenges. No one factor, there is no one silver bullet, there is no one factor that gives you a complete answer. But we think we're a reasonably big piece of the jigsaw puzzle, but that's why when we built our software, there is lots of ability to extract, push data out or push data in, so that the jigsaw puzzle becomes more complete, if you will. Let's take a look at some of the areas that I've already spoken to so that you can see it in action and how it works. So this is the Satalytics software suite. We've gathered the data. The data's come through. It's been crunched through the sausage machine or our analytics engine. And literally then in 3 to 4 hours, you're looking at some of the results. So you've got a two-factor authentication log on the left-hand side of the screen. There's a list of items that you might be performing, and you can hide that little menu to the left there. And one of the very first algorithms that we looked at was looking at methane detection. And this was looking at methane detection. You've already seen it ad nauseum. It's one of the basins in the United States. This was some of Anadarko's data set. And in this case, this was using 7.5 by 7.5 meter spatial resolution. And I believe that's way too coarse. And this was using the early SWIR capability of Satalytics, which was from the WorldView 3. And of course, as I said, we measure the gas plume, and you can literally click on any of that gas plume. We see to a low of 10 parts per million. We're looking at the column, 3.7 meter column, and we see to a flow rate in the local gas distribution down to 1 kilogram an hour. And Duke Energy, if anybody would like to speak with them, would be more than happy to show and talk to you about that. And also, of course, with our friends at BP, in the field, we tend to see more in the 20 to 25 meter, 25 ppm, and around the 10 to 15 kilogram per hour in those operations. But of course, it wasn't just, it didn't just sort of stop by looking at sort of that coarse resolution. It could have also been using Landsat that you've seen today. We let you set alerts and alarms and thresholds as to the sensitivity that you would like. Even you can choose, high, medium, and low as measurements. You can see the map on the right-hand side, the alerts on the left-hand side. I thought it was very interesting that many of our colleagues before had talked about looking at areas. Well, as you can see at the top here, as I ring fence an area, it will literally tell me what is flowing from that particular spotlighted area that I'm focusing in on. Or I could have simply said to show me all the high alerts in this particular area, or I could literally pick out a particular alert and alarm detail by knowing the number of the alert, or if I wanted to see, the whole area. So here's that alert. I click on that particular alert. It takes me into the area. I can see the source of the plume. We factor in wind velocity, wind direction, relative humidity. It'll give me a flow rate that's been calculated. You can see here. And then, of course, as you've seen me do before, you can click on any of the plume and it will give you the parts per million measurement that is coming out of that particular plume anywhere on the scene, or I could have ring fenced it to get the overall flow and volume that's coming out. We got a little feature that lets us have 2 screens. You'll see that in a second. Or indeed, I could have exported any of the imagery or any of the analytics. I could have said to Satalytics, just download all of that data, and it will spit it all out into something as simple as Excel if I wanted to spit it all out into another environment. Our first foray with BP, interestingly, nobody's spoken to this today, but our first foray with BP looking at methane was actually over water. And here in this particular case, if I choose, this happens to be Angola, and you can see here, the algorithms are two slightly different algorithms. As many will know, the reflectance of over water is a real challenge when measuring methane. But you can see here they both run simultaneously, and I can look at both the methane over land, or indeed, or excuse me, over water, or over vessel or land, as it would be, and it allows me to look at that particular type quarter. But to get it right up to date, where where we've driven some of this methane, which obviously has an enormous thirst in the boardroom around the world, and in local governments and people overseeing these areas, is that we want to get to a very accurate quantification. We want to understand our footprint, and we want to drive that down. So here I'm showing you that exact scene that I showed you in the PowerPoint slide, literally live. And there are two sources to the methane, as I said, we measure. Here we measure the gas plume itself, and every pixel that is 3.7 by 3.7 meters. Or, of course, it could have been the flow rate with the source, and you can see along this pipeline, here's the flow rate, 11 kilograms an hour. We take into account wind velocity, direction, and humidity. We got a little feature called Joule Maps. It defaults to being synchronized. You can unsynchronize that so that you can look at a different location. And now you've got side-by-side comparison, which could be different timelines, different areas, really entirely up to you as to how you want to look at that. Taking it one stage further, because upstream oil and gas production, whether we're looking at coal mines, mining operations, landfills, bodies of water, all can come from that Satellites data. This is the other side of the coin. This is the local gas distribution company that's delivering to your home. And clearly, Duke Energy, which is the largest utility in the United States, wants to eliminate leaks. So they have a grade 1, 2, and grade 1, 2, and 3 system. They have to respond to grade 1s within a certain number of hours, but their goal is to have 0 leaks. And as I said last week, there were a number of professors that were out in the field, one from Colorado State University, looking and ground truthing this, because quite frankly, they were pretty shocked at what they've been able to detect and from using satellite. But here you see that same plume. Of course, the numbers you're dealing with are much lower. And of course, the source of the leak with the flow rate and how it may appear from the subsurface. Same capability with that dual maps feature that lets us look at another particular area. So I may want to look at a different set of infrastructure in the second window, look at the plume, pick out any of the data sets, and the flow rate can be pushed to the screen. But from our perspective, the story doesn't end at where you identify the super emitters and how much. There's also another part of the equation where, in this case, one of our larger customers, which is BP around the world, they actually own a company called Finite Carbon, who are calculating the carbon offset. And so that's an extension of effectively what we do today with vegetation management. So here we're using what's often referred to as stereo pair, where now we're looking to get very accurate tree height and also speciation. So you can see the color codes as they look to calculate the offset of what they're admitting. And then in this particular case, and forgive me, I'm not sure why the grids are 16 meters by 16 meters, but we are part of that particular data feed. And in this particular case, we are feeding this data to this finite carbon. And if you click on every one of the 16 meter by 16 meter squares, basically we're giving you every tree, its speciation, its height, and its health in that particular block, no matter where it is on the scene. And all of that we're trying to accomplish within those 3 to 4 hours as a turnaround window for our clients. So let me just take you back. So let me just take you back. So let me.
Sean, my apologies, but could you somehow come to the end?
Yeah, sure.
Because
sure.
it's already 50 minutes and we will publish all slides, but just to still have time for Methane SAT to be presented.
So this
apologize.
That's okay. So in this particular case, what we're aiming to do is not just from an operational perspective, minimize the consequences. What you're seeing here, this is live data from Charlotte, North Carolina, where a pinhole leak in above grade gas operation caused the plume you see on the left. But the accuracy with which we measure, we want to be very accurate. And I'll finish with this slide in that these are blind tests and studies conducted in 2 different parts of the world, Spain and in the United States. We say we're sort of 10% either side of the number. The statistics would say that we're within 6 to 8%. And that's a little bit about Satalytics, and I greatly appreciate your time and attention.
Thank you.
Do you want me to proceed? This is Steve Hamburg. Can you hear me? Can you hear me?
Yes, we can hear you, and I believe that everybody can see your slides because we will share it from here,
Great.
from Vienna.
Thanks very much. And apologies for the confusion on my part this morning and then some logistical issues. I'm not quite up to snuff this morning, as we would say. So I just wanted to briefly talk about what Methane SAT. I know we have very little bit of time here. Next slide, please. So I'm Steve Hamburg. I'm the chief scientist at EDF, as well as the executive manager of Methane SAT. Since you've already heard about this, I'm not going to show all of this. The goal of Methane SAT was designed to allow us to quantify with a high degree of precision methane emissions from the oil and gas industry on a global basis in near real time, which we heard about from some of the other talks already. Next slide, please. And just as to remind us, which again, I won't spend much time on, that methane causes more than 25% of the existing warming and will dominate warming. Current emissions and their impact over the next couple of years will be dominated by methane. So if we want to do anything about the rate of warming over between now and 2050, our largest opportunity is with methane. Next slide, please. And that the oil and gas industry, if we just look at where we can reduce methane in the near term, the largest opportunities are in oil and gas. Next slide. Again, I'm conscious of time, so I just want to get into the meat of it. And we can look at the temperature implications of those, both from the economically feasible, the technological feasible, and the full mitigation. And we've modeled all of that, and we understand it. Next slide, please. And we heard a lot about about the need and the important work, for example, from Kairos about you looking for the ultra emitters, and it's critically important. One of the things we need to be really careful about is we do not understand the structure of emission patterns across different infrastructures. So depending on where you look, the relative role of the fat tail versus the main body of the distribution. And one thing we have found in all the studies across the globe, and now the hundreds and hundreds of people working on this, is there's a fat tail consistently across emissions distributions, but the shape of that fat tail is highly variable, and it's very hard to know what that relative proportion is. So it's critical that we understand total emissions, as well as, of course, large emissions. So this is really about how to create the data that allows us to be able to look at this problem, integrating all of the different potential sources of emissions and the structures of those emissions. Next slide, please. So what we need to know, and again, this is just repeating what we've already talked about, what's being emitted, where it's being emitted, how much is being emitted, and how that's changing over time. And we need to do that at fine spatial and temporal scales. And as was said again by many, remote sensing is really the tool that we're going to need to utilize for a lot of this. Having been involved in a lot of field work, working across many different portions of the supply chain, from local distribution to upstream to everything in between, we can't do enough studies fast enough to continue this. So remote sensing's got to be a critical, not sufficient, but a critical element of thinking about how to make these measurements. Next slide, please. And that we have to recognize that we're going to need multiple types of satellites with distinct capabilities if we're going to do this effectively. So this isn't, while I'm going to describe what I think is a pretty powerful tool in MethaneSAT, we're not looking at as MethaneSAT's going to solve all the problems, but it will in combination with a whole suite of different technologies. Next slide, please. And, you know, we can just look at, and I didn't include WorldView 3 here, but, you know, we know that there are a lot of different satellites with a lot of different capacities, and it's really trying to understand how we put all that together in a way that allow us to be able to do that with the analytics, as it was described, also with the integration that IMEO is doing, that Antoine mentioned, in addition to the work that they're doing directly. Is we're a big believer. I serve as chair of the Science Oversight Committee of IMEO, really trying to pull all these data together. And we've designed MethaneSAT to provide what we believe is the cutting edge of technology to allow us to be able to find and quantify emissions. And I'll talk why I think that's the case. Next slide, please. So the key here is we talked about we're talking about the worldview and the number of detections on, you know, what we can see. So MethaneSAT is a really high precision. It's the highest precision greenhouse gas measuring satellite. So we're looking at being able to detect delta methane at 3 parts per billion. And this is critically important. So this allows us to be able to measure across large areas with high precision so that we can detect total emissions from large areas and really quantify and answer the questions we've talked about before. But again, this is not everything. It's not a pure target mode with the kind of precision we just heard about from Satellites. But it does give us a total emission so we can really quantify what's going on and where it's happening. And this is really a critical element to it. It was designed, MethaneSAT 2 was designed explicitly to be able to quantify maximally effectively methane emissions from the oil and gas industry on a global basis, with a goal of being able to quantify emissions from at least 80% of global production. And as I said, obviously oil offshore is important. Doing glint mode is critically important. That will not happen immediately, but it will be soon thereafter. Next slide, please. And so one of the points that has already been talked about to some degree, one is the difference between global mappers like TRPOMI, point source detectors like GHGSAT, or we just heard about in WorldView 3, is they're both useful, but they don't allow, neither one of us allows us to really get the whole picture. TRPOMI is a really great, powerful instrument, allowing this incredible work that Kairos described on this near real time of ultra emitters, but it doesn't allow us to see the detection threshold is high enough so that we're going to miss a lot what's going on. And of course, we don't have the spatial resolution. We have to use others. Point source detections are really important to give you that granularity, but it's very hard to track total emissions changes and how things are dynamic in the larger sense, because we know there's a tremendous amount of intermittency, that not everything is emitting constantly. We get a lot of things turning on and off. And so we really want to be able to say how much is the total, and then what are the specifics below that total, and how does the individual points add up to the total. And as Antoine talked about, we need to really worry about, are we seeing the overall trends that are required, whether it's from the global methane pledge or just for good action, and so that we can really get to the lower emissions that we need if we're going to have any hope of reducing, let alone stabilizing the climate rate of increase, let alone stabilizing the climate. Next slide, please. So we really wanted to create a satellite that really puts together the strengths of both a mapper and a point source target mode instrument, which we've done. I have a little video that I pulled out because I needed to send the slides and it was too big. But it really allows us to get that level of granularity. And as I mentioned, we're looking at a precision of 3 parts per billion. We have an inherent pixel size of 100 by 400 meters. Now, we don't get the full resolution of that 3 parts per billion within every 100 by 400 meter, but it does allow us to get a lot of spatial granularity, which allows us then to be able to really map, as you can see in the image here, a heat map of across the 200-kilometer swath of the satellite, which really gives us a patterning similar to Tropomi, but much, much finer grain. So we really begin to understand where those emissions and how they're changing. And we'll be able to do that repeatedly. Next slide, please. So we'll be obviously quantifying emissions. We're doing full inversions. So the basic data product will be an L4 product with full inversions. That's what we released. We will be able to cover the globe roughly a repeat time of every 3 to 4 days. And all of this will be a cloud-based automated analysis system so that all the data is collected and automatically analyzed and producing this data product and making it available free of charge to the world. Next slide, please. And then just as we think about this as just some of the inversion, this is a paper we did now a couple of years ago showing the power of this approach using the early Tropomi data, integrating it for the Permian Basin, which again has already been described. Next slide, please. And we get this very, very important data, but of course, very coarse data on the right, where the posterior is showing about 2.9. And I'm sure I missed part of what Antoine said, but he talked about some of the inversions, and they've been doing a lot of this work since then as well. Next slide, please. And the key is, of course, the incredible complexity of the infrastructure there. And the key is to remember that the small emitters in the US, the large number of marginal wells, which makes up the overwhelming majority of the facilities in the US, account for about half the emissions, but only 6% of production, or less than 6% of production. So we can't just be looking for things that are large. We have to think about lots of small sources because they add up to a large proportion of the problem, at least in some geographies. But we believe in many geographies. Next slide, please. And of course, as was already mentioned, the temporal dynamics are critically important, and we need to be able to measure them quantitatively and over large areas. This is just some of the data we collected in the Permian using towers and air overflights, showing the very dynamic nature of emissions associated with the COVID crisis, which I'm getting to personally experience at the moment. And we need to be able to do this from space. And we believe with Methane-SAT, we'll be able to start to produce these data from space with a high degree of integrity. Next slide, please. And I'm just going to pass over it. We all know this site level, we just heard about it. All the data will be free of charge to everybody. The only restriction will be if you want to commercialize it, you have to sign, you have to come to an agreement, meaning any commercial company can have it. You can't resell it without permission. Next slide, please. And then we've basically mapped the entire globe for all the oil and gas production to meet that goal that we said for at least to 80%. And we have these 200 by 200 kilometer pixels. Here you just see a map of what the production is and where we'll be viewing around the world. Next slide, please. And then we can look at just the different types of oil and gas infrastructure. We're also mapping all of the oil and gas infrastructure around the world that will be publicly available so that one can see what's underneath every of the tiles. And as the data produced, so you'll know both how much is being emitted, what is it point sources where we can identify, and what are the different infrastructures underlying more diffuse sources so that we can get the total picture and you understand what the infrastructure associated with those emissions will be. Next slide, please. Sorry, I didn't want to keep going. Next slide, please. Thought I cut this one out. And then we just have, of course, we have the global mappers, as we talked about, groups instruments like TRPOMI, GSAT, GOSAT, GW will be flying next year. We have Methane SAT, which will allow us to be sort of in between. And then this target mode instruments like GHGSAT, Carbon Mapper, Atlantis, that will be either are flying or will be flying. And it's that combination that gives us really the power of being able to do total emissions and understanding how they're changing and what technology and which specific ones. And there's obviously others that aren't included here. Next slide, please. The key is, of course, that we have to work together and create this ecosystem of data that will allow us to really provide the most insight on a global basis. Next slide, please. I realize we're almost out of time, essentially are out of time. And with that, thanks very much. Sorry for the difficulty joining and the very whirlwind approach to this.
Thank you very much, Stephen. It was a really nice overview for last slides to show after the end of today's webinar. My only question is actually, you always mention it will be so like in future
Yes.
time. So
Yes,
did I
my
understand
apologies.
correctly?
Yes,
So
my apologies.
when
Launched in a year from now.
in 1 year from now, so it will
Yes.
be in operation. Okay.
Yes.
Okay.
Yeah,
Great. Great to know.
it's fully built, and we're now just integrating everything and doing the full testing.
Okay. Okay. Thank you very much. So yes, we are we are almost at the end of the time foreseen for today, but maybe still time for question if somebody would like to put it on. So just raise hand and unmute yourself. So it seems no raised hand. Some questions were answered before in chat. I have to say for myself that actually I learned a lot today, because it was always mentioning satellites and different projects and different names actually. But now we got more closer picture, like what shall be in place, how to combine it, what type of software is also needed. And then it opens much more questions, like all this is fine, all this is in place, and let's see who is use it and who can actually make best of use of all this data, with the common goal to decrease these emissions. But maybe this will be for one of the next webinars. So with this one, I would like to say that we will now have a break for 2 months. We will not have Methane Mondays, and then we will continue in autumn, first in September, and I think it depends very much on Marco Gas and GIE if best available techniques will be ready by then. If not, we will find some other topics. And with that, I would like to say that yes, slides will be shared and the webinar is recorded, so it can be found at the Energy Community site, but also at GIE and Marco Gas. We will see what other topics will be of interest in autumn. And with that, I would like to thank very much our presenters today, and to thank also participants of today, but also following us through all this 12 Methane Mondays. It seems that it's still useful, so that's why we will continue. In the meantime, stay healthy and well, and recover as wish for Stephen first, and have relaxing, inspiring summer.
Thank you. Goodbye.